I am absolutely honored to introduce Professor Ahmed Younes. He is a professor of quantum computing and the Vice Dean for Education and Student Affairs at the Alexandria University in Egypt. And he's actually also part of the Alexandria Quantum Computing Group. And I'm sure he will tell us a little bit more about that later. We're just absolutely looking forward to hearing from you about the foundations and applications of quantum computing today. I feel like everybody's waiting for that.
Okay, thank you, Nada, very much. Thank you, Dr. Faisal. Thank you, Dave. Thank you for inviting me to this talk. Actually, I'm really excited to give this talk in the Middle East and South Asia Quantum Computing Meetup and Washington, D.C. Quantum Computing Meetup. Actually, today will be more about introduction to quantum computing with little bit tricks on how to start, how to understand this topic, and let's start. I prefer usually to start with a little bit history to understand why we are here, why we reach to the stage of quantum computing, why there is a need, why there is a transition that we have to do using quantum computing. So the history starts when they invented transistors in 1947, and to invent new families of computers, of microprocessor, they have to increase the number of transistors to make the digital circuits more complex, to do more functions. So to do this, they were restricted to use the same physical space, because if you check any CPU, any microprocessor, it is always the same physical size. So they have to increase the number of transistors on approximately the same physical space. They do this by a trick called miniaturization, is to make the transistor smaller and smaller so they can increase the number of the transistor. But actually, one of the founders of Intel, Moore, notes that actually people can double the number of transistors on approximately the same physical space every year. Actually, these notes found to be valid from this date till today, till maybe before this date. Actually, this is the miniaturization, is to we can always double the size of the transistors every year, every 15 months approximately. We note this in everything in technology, if you agree with me. Actually, this graph shows the number of transistors in the processors over years. And the last processor we know as a new processor, as a new architecture, was Pentium 4 in Intel, of course. Did anyone see any architecture in Intel after Pentium 4? Actually, we don't. Why? Because they cannot make a new architecture. They are selling old CPUs now. They are selling dual core. They are selling quad core. They are selling old processors as 2 processor or 4 or quad core or octa core or so. So actually, by this date, we are facing a challenge that our industry is coming to an end. Why? Because according to Moore's law, the number of atoms per bit, because they are decreasing the size of the transistor, actually the number of atoms will be only 1 atom by actually 2015, 2020. This is a quantum level. This where we cannot control the bit by our classical mechanics anymore. This is a challenge. So we have to decide to stop any development in the field of computer science, or to go to another alternative. We have to find another alternative to keep the technology going on. So we need alternatives. people start to think about this actually long time ago, and one of them is quantum computer. Actually, one of the good alternatives is a quantum computing, but we have to mention that we have more than one alternative. For example, we have DNA computer, we have enzyme computer, we have many people are trying to find alternatives, but actually the one that's close to industry, that is we can see the results, is quantum computer. So quantum computer is the nominated alternative for the digital computer we know nowadays. How the quantum computer starts? Actually, it starts by a publication by Richard Feynman in 1982. He was trying to do some kind of simulation on our classical computer, the digital computer, on quantum mechanics, but he didn't succeed to do the simulation. So he didn't stop with his failure to do the simulation. He published a very nice paper proposing that, okay, I didn't do this experiment, but what if the computer is working with the rules of quantum computers? Sorry, the rules of quantum mechanics. So is it going to be more efficient? Is it going to be any benefits from using this quantum mechanics in computation? But actually, no one could understand what's the benefit. How can we do this? Maybe from 1982, maybe in 1985, Deutsch proposed his algorithm, Deutsch algorithm, and he proposed what we call quantum Turing machine, which he proved that actually this device is a general purpose, is a programmable device. So we can use this to solve problem, but no one know how to solve problems on this new architecture until 1995, when Peter Shor surprised the world by his algorithm to solve the integer factorization problem. Let me quickly tell you what is the integer factorization problem, why it is very important in computer science. The integer factorization problem is that if you have two prime numbers, b and q, multiplied by each other, and we have n. What if I hide b and q from you and give you n? B and q must be prime numbers. So, and I asked you, can you find b and q from n? Actually, this problem is very hard. It is classified NB on classical computer because the best known algorithm to solve this problem is with this complexity. N here is the number of digits of the number we are trying to factorize. Just to know why this problem is important in computer science, I have to tell you that all the online transactions are protected by this problem. The RSA encryption are based on this. RSA encryption is the encryption used on all online transactions. It is when you have your websites, HTTP or HTTPS. This security is based on how hard it is to factorize this problem. The people who invented this algorithm, this encryption algorithm, showed us, just to show how powerful their algorithm is. They published this number RSA129 in the middle 70, I think, and they challenged the world that time. Can anyone factorize this number to their two prime factors? Actually, the solution is known now. We know that these two prime numbers we see, their multiplication will give this. But how did we reach? How did we find these two prime numbers? Actually, no one can break this RSA 129 until 1994. Actually, group could factorize this number using 1600 workstations working for 8 months. So this shows us that how hard this problem is. Actually, if we have a number not 120 digit, 129 digit, but 250 digit, using the same technique, we will need this number of years to factorize this number. And if we have a number with 1,000 digit, we will need 10 to the power 25 years, which is significantly larger than or longer than the edge of the known universe we know at least. What Peter Shor did in the integral factorization problem, okay, this is a current challenge. If you are interested in such problems, this is a current challenge, RSA 2048. If you are interested to factorize this number, the organization who published this number offer you a prize with 200,000 US dollars. So you can start working on it if you have time. But actually, you can use quantum computer to solve this problem. Because Peter Shor invented an algorithm, a quantum algorithm that works only on quantum computers that can factorize this 1,000-digit number only in 20 minutes if we have a real quantum computer in today. So actually using this based on this result, the people are surprised that actually our encryption algorithms, our public key distribution algorithms are no longer safe. And is it safe now? Actually, I cannot tell. Do we have a real quantum computer working and can break our public key distribution algorithm? No one can tell. But the good news that we have a good encryption algorithms using quantum computer in unbreakable codes using quantum computers. After Peter Shor's algorithms, this huge result, we will try to we have a potential power in this device we have to explore. We have to try to find what else we can do with this device. Next year, Love Groover described an algorithm, a search algorithm, a quantum search algorithm that can solve the unstructured search problem in square root n. The best known classical algorithm on classical computer needs order n steps if we have a list of size n. So this is a quadratic speed up over classical computer. Actually, these two algorithms, after these two algorithms, the people are trying to, okay, we have something here. We have a device to explore. We have power to try to use to solve problem. So after these two algorithms, people are trying to find what quantum can do in any branch in computer science. If you go online today on Google and just type quantum before your favorite computer science subject, you will find people do something on this. So actually, we have to be clear about this. I believe that we are now in the period of transition from computer science to quantum computer science. Everything is moving to quantum computer science. Here, I provide you with a very nice website I use to check frequently, which is Quantum Computing Reports. It will tell you what are the universities working on this. So you can check and see that many universities are working now on this subject. So it is not something new to say that, okay, this is new, I will wait until it is popular. No, actually, all universities are working on this subject now. And this is a very good table to show the power we can gain from this quantum computer device. Actually, this link I used to check frequently as well, which is Quantum Zoo. It shows the algorithms which people invented on quantum computers. They are trying to solve problem with speed up over the classical algorithm. So I recommend you, if you are trying to work on any problem on quantum computer, just to check this website first. It will show you the progress on almost all quantum algorithms. People are trying to find what is the problem, what is the speed up. The best thing in this site is that it gives you reference. So you can check before you start. You have to know what people did in this problem with reference. So you will find people solved many problems or trying to solve many problems on quantum computers, and always we have speed up or over classical computer. So this is something we have to take into consideration. Another thing we have to take in consideration if you are interested to learn about quantum computing is that, okay, my background is computer science, but we have to say that mathematics is very important in quantum computing. In this table, I show you the fields of in the topics, in the mathematical topics, and their importance in quantum computing. Actually, I don't want to scare people, but you have to know about mathematics to be to learn to understand the power you can gain from quantum computer. You have this is not the whole table, so you can just check this in blue. And if you know quantum computing, you'll understand what I'm talking about. But just check these mathematical topics, and the list is long. Actually, we need all mathematical topics to understand quantum computing. We don't have to be expert in mathematics in all these fields, but at least you know the basics, so you can explore more if you need to solve something on quantum computer. So this is the topics I think which is important in quantum computing. So mathematics is important. We have to admit this. We cannot change this, and it is very important. So D-Wave was the first device of the first quantum computer announced to be a working quantum computer. Maybe you have pros or cons on this, but it is the first one. They were brave to announce to start this industry, and after that, many quantum computers come to life. It is not research anymore. It is not in the lab anymore. Actually, you have many startups, companies in these fields. And you can check also in this website, the quantum computing reports, that we have, that we have many startups all over the world. So if you didn't have your startup, do your startup now. You have many companies all over the world which are working in quantum computing in different specialties, and there are many jobs. If you are interested to check this, sorry. If you are interested to check this, if you have a background of computer science, you will find people are searching for the same jobs as computer science, but with quantum before this job. So we have many jobs. You have to start learning about quantum computing, because I'm sorry to tell you again that classical computer will be obsolete very soon.
Ahmed, you have exciting words and you know your stuff. I think that you might be generating some questions from the audience. I'm not sure, but this might be a natural point in time for Faisal to share any comments or any information. Before you do that, though, Faisal, Nada, I was watching the expression on your face and saw that you're into this as I am. Do you have any comments at this moment, or should we turn it over to Faisal?
No, I find it very, very exciting, and I don't know. I guess I feel like I'm not always super conscious of the fact that I did work on one of the very first quantum computers. So it was kind of nice to see that in
Is it on the
person.
list? Is it on Ahmed's list?
I mean, we worked on the D-Wave machine. So that's, we optimized our problem on the D-Wave machine. So it was just a cool moment.
And I think that's very good because it's inspirational for other young people to know that in our group, this is all possible. So I'll turn it over to you, Faisal. Were there any comments or questions?
Thanks, Dave. Yes, there are a couple of questions that I thought would be, and there's another one just popped up. So let's see. One of the questions for Professor Younes is the following. Is the Fourier transform playing a major role in Shor's algorithm? And then there's a comment, interesting, with 3 exclamation marks. This is from
Actually, in Fourier transform has a quantum version, which is a quantum Fourier transform, which is the heart of Shor's algorithm. Without the quantum Fourier transform, where Shor's algorithm could not solve the problem. So yes, it plays a major role in Shor's algorithm.
Wonderful. Thank you, Ahmed, for that answer. And thank you to Charnia for that question. Another question that we have is from Khaled Hindi, which says, are we able in Egypt to build our quantum devices ourselves?
Actually, this is very interesting question. I'd like to know the answer by myself.
Me too.
Okay.
If you know the answer, I'll be glad to hear. So actually, the interest in quantum computing in the whole world is increasing, and I think everyone will be able to build a quantum computer. It's not that hard. It just needs experts to do the job.
So I guess the follow-up question I'm imagining from Khalid would be, do we have experts in Egypt who can do that?
We are trying to develop the expert to do the job in Egypt. So we hope soon we will try to invent quantum devices, maybe not quantum computers yet, but at least quantum devices, because we have the expert to do this.
Wonderful. Thank you, Ahmed, for that question. Just one last one for now from Vishal Bajpayee. The question is, any tips to start off your career in quantum computing as a developer?
Actually, yes. To start quantum computing as a developer, you have to choose your favorite quantum computer device, which we will show shortly. Second, you have to know the basics of computer science, the basics of development, at least as a computer science computer programmer. Python is the best programming language to start working on quantum computers now. You have to know more about mathematics, as I said, and you have to choose your field, because it is not quantum computing now. You have to quantum image processing, quantum database, quantum machine learning, quantum what? You have to be a developer on some field similar to the computer science. So I know if I did answer his question.
I believe you did, I think. So just one last one. Another one popped up just quickly. It's relevant now. The question is, would you show the second slide on the mathematics skills required?
Sure. So this is the first, and this is the second. So what's...
the question was just to show the slide. So let me see if there was anything specific.
As a mathematician, I can vouch that all of these are important.
As a computer scientist, I say the same. Mathematics is very important. And if we say that mathematics is not important in computer science, then we are cheating ourselves.
Yeah. I'm going to make an observation here. I can see that there is a quantum walk Nada, could you give us a demonstration of a quantum walk like an Egyptian?
Maybe one where my hands are simultaneously this way and this way.
Pharaonic walk, not Egyptian walk.
All at once.
Quantum superposition of both, yeah, both systems.
I see another question about the programming language, and I will show you shortly about the known programming languages used today on quantum computers.
One of them is definitely Python.
Continue.
For sure.
Yes, please. Yeah, go ahead.
I don't see any questions now. Okay.
No.
So this is the startups, and this is the programming languages. We have many programming languages now in quantum computing. Maybe the most known programming languages are the Qiskit group used on IBM quantum computer and Cirq on Google quantum computer. We have actually, the list is much more than this, and every few months we know that there is new quantum programming languages. Actually, don't be scared to learn any of these, because they most of them are Python-like programming languages. So the programming is easy. It's not that hard to learn. You need to learn the basics of quantum computing to be able to code to use these programming languages. Okay, I see many questions showed up. So before I start with the quantum data, I'd like to see the questions again.
Oops, sorry. I can read the one from Zur Sayag, which says, I asked in the other chat about randomness not being used by most people where it is now available PPL. I'm not sure what that stands for.
People.
Oh, people. Okay. Still use
resident young person.
There we go. Thank you, Nada. So I suppose the question is, do people still use pseudo-random number generators?
Still use. Actually, people will never stop using random number generators. And the good news that we have true random number generators, quantum random number generators. Using a classical computer, we can do no better than pseudo random number, but on quantum computer we actually can do real random number generators, and it is important in many fields. I cannot list them all now. This is something we will never stop using.
And there are a couple of more questions, but I'll ask raise the one from Lawrence. It says, are these programming languages that you just referred to, Professor Younes, tied to the associated hardware?
For now, yes, because every quantum computer has his own architecture, so there is some constraints on the programming language. It is more like the assembly programming language on classical computer. It is machine dependent. Till now, it is machine dependent. We are working hard to have a high level programming language, a high level quantum programming language, but it is not available yet. It always tied associated with a certain hardware. Yes.
Wonderful. The questions are going to come in continuously, but I suppose we can move on forward, Professor Younes, and then come back after a little bit and address all these questions.
Okay. So I'd like to explain quickly why this device is that powerful. Actually, I cannot answer this question quickly as I promised, because I can tell you one or two things that make this device can compute faster than the classical computer. The first thing is quantum data. How do we represent quantum data on the quantum computer? Just to understand the difference between the basic unit of information in classical computer and in quantum computer, we have just to remember that the basic unit in classical computer is a classical bit. which can be in one of two states, one at a time, 0 or 1. But we have on quantum computer what we call a qubit, a quantum bit. Quantum bit is different from the classical bit, is that it can be in a superposition of both 0 and 1 at the same time. So classically, we can be the bit can be in 0 or 1, but on quantum computer, the qubit can be in a superposition of both. How can we do this? Actually, there are many ways to do this qubit thing. One of them is the trapped ion experiment. The qubit is just an atom. The 0 is when an electron in the ground state, and if we just excite this electron with a light pulse to jump to the higher level, so it is in the 1 state. So this is 0 state, this is 1 state. The interesting thing in quantum computing is that what if we excite this electron not with the full energy it needs to jump to the higher energy state? So what about if we halve the energy or 1/3 of the energy? So actually it will start, it cannot stay here if we, the energy here is, let me show this on my small whiteboard. I think it will be more clear. So if we have an electron here, and we have two energy levels, and we say that, okay, if this electron in the low energy level or the ground state, so we will call this 0. Oops, sorry. And if the electron in the upper energy level, so we will call this in state 1. And to move the electron from state 0 to state 1, actually we can we need energy, which is the difference between the two energy levels, E1 and E2. So if we laser beam with this energy, it will go. This is a really simplified version of what's going on, but just to understand what is the concept. So if we put a light pulse or laser on this electron, it will jump and be on the upper energy level. This is what can we do on classical computers, 0 and 1. What's new? What if we have electron here and we put not energy, the full energy, but quarter the energy? What will happen? So actually, it will not be able to stable on the higher energy level and cannot stay on the lower energy level, right? Actually, it will start to oscillate between the upper and the lower in a motion depends on this energy. So actually, if we open the door, this must be a closed system, by the way. So if we open the door on this system, you might find the qubit on the upper energy level, which is 1, or the lower energy level, which is 0. The expert in quantum information theory says that when you measure the qubit and find it in 0 or 1 in a probabilistic way, so actually it is in both states at the same time. So actually, this is not the only way to do the qubit. We have another experiment, the nuclear magnetic resonance. The qubit, the state 0 and 1, is set by the spinning of the qubit itself. These two examples, but actually the race to find what is the best technology to build the quantum computer is on. If you check, just write qubit, and this table is in Wikipedia. It's not. You don't have to go to some kind of reference or scientific paper or something. This 0 thing and this 1 thing as a quantum system, there are many possible technologies to manufacture this quantum computer. And the good news is that it turns out that not only one technology is possible to build this quantum computer, but many technology can be used to build this quantum computer. So when you go to the market and buy your quantum computer, you have to ask, what is the technology used? So don't go and buy your quantum computer. You have to ask, is it photonic quantum computer, or it is superconducting quantum computer, because everyone has his strengths and weakness till now. So this is surprising that we can have many technologies to build the quantum computer. And this is the most famous technologies used on the market today, because we actually have quantum computers you can use today. For example, Google quantum computer, IBM, are using the superconducting qubits. IonQ is using trapped ions technology. Intel is trying to use silicon quantum dots. Microsoft is trying to prove that topological qubits is working. They didn't do this yet fully, but they are working on technology called topological qubits. Actually, we have many technologies which can be used to build this quantum computer. What is the benefits? Actually, let me go back again to my whiteboard. If you have 3 classical bits, not qubits, 3 classical bits, actually these 3 classical bits can be in one of the 2 to the power n states one at a time. So it cannot be, it can be in one only out of these 2 to the power n states. But if you have 3 qubits, so actually you have the 2 to the power n states simultaneously. You have the whole possibilities simultaneously in a superposition. So instead of doing an operation step by step over this array, you can do it once on quantum computers. This is huge speed up. So no matter how long is this list, you can do just once. Okay, this is not the end of the story. We have another problem, how to get useful information, but actually we are applying this simultaneously on all the data. I'd like to show you some tricks on quantum computing, but I'd like to see if we have questions first, because I see long lists of questions and I'm happy with that.
Yes, absolutely. Thank you, Professor Younes, for giving us this break to address some questions here. Nada, would you like to read them?
I'd love to. Okay.
Right. So they should show up, right, as the ones that are being addressed live.
The open questions. Okay. Should I go with the more technical ones first, or just like in chronological order? Okay. Okay. So we have a question from Yahya, who says, "Is learning quantum going to help me as a data science student?"
Actually, let me tell you, Yahya. I was in October 2019, I think, in China. I was visiting a big university there, working in big data analytics, and I visited this big exhibition, big data exhibition. And there was a picture. I can bring you this picture, but what's important in this picture, that China believes that which is the biggest big data market, believes that the next generation of technology will depend on 5G technology, blockchain, Internet of Things, and quantum computing. So you have to master these 4 things, because these 4 things will change the way we know quantum computers. So quantum, again, 5G technology, blockchain, Internet of Things, and quantum computing.
Wonderful. Thank you, Doctor. I also was in China, and they did definitely put a lot of stress on those things when we were there. Okay, we have a few questions that are asking to repeat certain slides. I want to ask on behalf of everybody, will the slides be available for the attendees?
Yeah, sure. I will send you the slides so you can find it will take you as a guide to know which topic in math you will need to learn what. Yes, okay, I'll send it to you.
Okay, great. While we're on the topic of slides, Saif asks, What do the colors represent on the slide about the programming languages? So there were multiple colors from red.
Okay, it is just survey about if there is README for this file, change log. If you change your code, is there any available tutorial? So if you have a green in everything, so it is very good programming language. So these colors is just for these topics. It is those kind of surveys on the current programming language. So just like this.
Oh, great. Something like an ease of use. Okay. Question from Sur.
Yes.
Thank you for the reply. I meant if you can explain how come people don't use true randomness, as in dwarves, and does it make a real change in random-based algorithms like random walks, etc.?
I'm afraid I didn't get the question. Is it a comment or a question?
I think he's asking for an explanation as to why people don't use true randomness.
Why people don't use true randomness? Well, I don't know. Why people don't use true randomness?
Yeah,
I
so
believe
this
people,
is sorry.
they use true randomness actually.
So this is a follow-up question from Zur. He had asked about randomness earlier, and I think he's clarifying what the question was. I think the question is, does it make a big difference in random-based algorithms like random walks if you use QRNG, for example, quantum random number generators versus pseudo-random number generators?
Actually, if we can use true randomness, it will be much better. So if we have a source that generate random number, true random number, we will never go to the pseudo random number. We are trying to simulate, and there are tests to check if this pseudo random number are close to the true random number or not. So if they are close to the true random number, okay, we will go with these numbers. If they are not, then we will throw them away. So we use true random number if they are available.
Wonderful. If I can just add a few words here.
Yeah, sure.
Yeah. So QRNG, or quantum random number generators, quantum sourced random numbers are actually very useful already. They're commercially available products and algorithms that use them. The most important, most relevant use of them is actually in cybersecurity, where you like to use them to make sure your encrypted data doesn't leave any pattern behind, right? Because if you have encrypted data that has a pattern, some suitably funded and motivated opponent will actually spend a lot of time, they're dedicated, they'll figure out what the patterns are and try to reverse engineer what the original code was, right? Or the original message was. So QRNG definitely are useful from that point of view, but generally speaking, I suppose one could argue that the more randomness you have in the sense of being true randomness, that can only be a good thing. Thank you, Professor Younes. Another, please go ahead.
Questions from Charan. I'm so sorry. Charan. I'm having so much trouble.
Okay.
Charania.
Question. Charan. Okay. Does the qubit use the same concept as a simulated emission of laser? And I guess a follow-up would be, is the qubit oscillating between 0 and 1?
One of them, yes, actually. Qubit, as I mentioned, there are many possible technologies to build this qubit technology. Trapped ions, we will, the emission of laser, we will read the photon emitted from the electron on this controller to understand the information in the qubit. So actually, yes, this is one of the possible ways to read the data from qubit.
Okay, I think a follow-up question for that was, is the qubit going to be oscillating between 0 and 1 when the laser energy is applied?
Sorry?
I'm sorry if my audio is
no, it's okay.
affected. Is the qubit going to oscillate between 0 and 1 when the laser energy is applied?
Yes, if the laser energy is not enough to make this electron stable on the upper energy level, it must oscillate between 0 and 1 until we open the door, do the measurement thing to understand if it is 0 or 1. So it will oscillate, yes.
Okay. And I think there's 2 more questions. Are there any problems? This one I'm actually interested in. Are there any problems in computer science that are proven to have better time complexity in classical architectures than in quantum computing paradigm? Or is it guaranteed that the quantum computer is not worse than classical?
You mean in classical better than in quantum?
Yes. So Safe is asking, are there any problems where classical computing is better than quantum computing? Or is it proven that quantum computing is not worse?
Actually, so far we didn't find any problem with the same speed up. Always quantum computing wins the race. So at least if they didn't solve the problem in a faster way, it will do with the same speed. So no, I don't believe that classical computer can win in any problem because it is subset of quantum computing. The basic reference to us is the Turing machines. So to do things solvable on Turing machine, we can do it on classical computer or quantum computer. But quantum computer always has advantage over classical computer.
If I may interject, Dada?
Yeah, of course.
Kind of maybe address this from a slightly different point of view. So certainly agree with Professor Younes on what he said, but there's a slight side question, which is like, if somebody's trying to build a quantum computer, as many people are, and Professor Younes addressed some of the companies that are involved in that. So that takes on a different issue, right? Where you have the idea that depending on the particular technology being used, are you actually seeing some speed up in that technology versus another technology? So it's not so much, in this case, whether you're theoretically addressing.
Yeah, theoretically, quantum computing wins the race because it is complexity. We measure complexity of the algorithms. But as a technology, yeah, I think quantum computing is still early to solve useful. Not early, in a few years, 2 or 3 years, we will be able to use quantum computer to solve real problems. But today's technology in quantum computer, no, we cannot solve useful problems with useful data so far. But this doesn't. It's not a limit in quantum computing. It is limit on the architecture, on the current technology. So I cannot say that quantum computing is weaker than classical computer. This is not correct. The technology says this.
We'll catch up soon. Okay, I want to say thank you, Sharon. It's very nice to meet you, and I'm so sorry for butchering your name earlier. Should I move on with the rest of the questions, or do we? Okay. So what about cybersecurity future in quantum computing?
I will answer this shortly, yeah, in a few slides. Yeah.
We'll look forward to that. Do you think that blockchain technology will be replaced or to some degree be changed once quantum computing is mature, as quantum has true advances?
For quantum blockchain technology. There is quantum blockchain technology now, so it will be replaced.
Yeah. Perfect. Yeah. Another question that says, a few days ago, Google has said that it's quantum has resolved an equation within 2 seconds that takes thousands of years on a regular computer. Intel has relied that they have resolved it on a supercomputer within 2 days. If a supercomputer is powerful like that, why don't we see it in stores, especially if it's built from a simple Raspberry Pi?
Actually, because of the price of the refrigerator. Actually, the most expensive part in quantum computers now is the refrigerator, because they must be kept cold, very cold, for the energy not to interfere with the quantum data. So when it is affordable, actually, I will be the first one to buy it.
Okay, final question that I see from George. Space complexity of quantum computing, bandwidth between quantum and classical worlds. I think there's a question there about the space complexity of quantum computing.
I didn't get this question. If you can, in our next break, if you can rewrite the question, I will be glad to answer this.
Okay.
Okay. So let's move on. We have many things to say.
Yes.
Okay. So how do we represent this classical, this qubit mathematically? I will not go deep in mathematics, just to make you get little points on this. So we have now a state which we have qubit in the low energy level, and another one which is in the higher energy level, and it may be in between, right? So it can be oscillating between this and this. In this case, it can be in zero state or in one state. So to represent this, we write a linear combination between this zero and this one. So we write it this way. Quantum physics used to write this way using Dirac notation. A0 plus B1. These 0 and 1 things I will tell you about in 1 minute. But let me tell you what is this A and B. A and B are the amplitudes of these states. It is their square, or these are complex number actually. So they represent somehow, without going in details, the probability to find the qubit in state 0 or in state 1 when we open the door to measure it. What is these things? Actually, these are vectors. And why we write it this way? Because it is more compact way to write using Dirac notation. So just remember for now that this 0 will always to refer to this vector, and 1 will refer to this vector, because we will need this in a minute. So 0 always refer to this vector, and 1 always refer to this vector. So to summarize, as a difference in classical computation, we have 0 and 1. In quantum computation, we have a linear combination between the two states. It can be in a superposition between 0 and 1 at the same time. So we have our data, but what about the operations? On classical computers, we use the gates, the logic gates, the and, or, not, and all these logic gates, which is common now, we all know. But on quantum computer, we have a different type of gates, which is unitary matrices. Why it is unitary, I will tell you in a minute. But these gates looks like this. It must be unitary. It will do logical operation, but in a quantum way. So to understand what's the difference between these gates and the classical gates, I will tell you a trick to be able to understand these matrices in very easy way. So if we have not classically, if we have not, we all know that not, we have input, we have output, right? So we have 0, the output will be 1, 1 will output will be 0. This classical gate we represent graphically in this way as a digital circuit, right? What about the quantum version of the not? We have a quantum version of the not, but the quantum version, we write it this way as a matrix, right? So how do we read this matrix in very easy way? If you imagine that this is the input, the column, this is outside the matrix. So if we have 0 here as an input, the vector below the input will be the output. You can read this way. So you can see the truth table in the matrix itself. So it's not just a normal matrix. You can understand the logic of the gate from the matrix itself. So what about this? This is the matrix. If we go back one step, you remember that 0 is this vector, 1 is this vector. So actually this vector is the 1. So if the input is 0, the output is 1. If the input is 1, the output is 0. So you can look to the matrix and understand the logic behind this gate. For example, we have another gate, important gate I would like to show. This is a Hadamard gate. So what is the input and output in this case? So this is one of the difference. It is not only logic inputs and outputs. So 1 over square root 2, sorry. So what is the input and outputs here? Again, if this is the input, the output will be this vector. If this is the input, the output will be this vector. So what is the vector? So the input, if the input is 0, the output will be 1 over square root 2, this vector, right? So what is this vector? Always try to search for these two vectors, zeros and 1, in the output. So actually we can write these vectors this way, right? 0 plus 1. So actually these vectors we are looking for showed in the equation. So it is 1 over square root 2, 0 plus 1. So this simple gate created you a perfect superposition. It is a perfect superposition between 0 and 1. Actually, this very gate which we use to create true random numbers, because the probability to find 0 and 1 or 1 is half, exactly half, which is very powerful to generate random numbers. So these matrices, you can look and see the truth table in this. Not every matrix is can be applied on quantum computing. The matrix must be unitary matrix. What is a unitary matrix? It is the matrix that satisfy this condition. I will not go deep in the mathematics of this. These more gates, and you can look at any matrix now, and you can guess what is the input, what is the output. So if the, for example, the Z gate, if the input is 0, the output will be the same. If the output is 1, the output will be this vector. So I'm just trying to tell you how to look to the matrices, because to see the logic in the matrices, it is not a matrix in the linear algebra course or something like this. We have many matrices actually, and when we go higher, over 2 qubits or 3 qubits or 4 qubits, the matrices start to become bigger. So we try to find simpler way to understand them. For example, this gate is a C0 gate. It is applied on 2 qubits. If we have here control and the target. So if the control is 1, the target will be flipped. Away from the matrices things, we can understand this logic very easy. I will tell you, this is a gate, this is a control, this is a target. So the data flows this way. So this is if the input is 1, 0, for example, the logic of the gate states that if the control is 1, then flip the target. This is a control qubit. So it looks like as an if statement, right? It is if control is 1, then the target will be flipped. If the control is 0, the target will stay unchanged. Nothing will happen to the control. So this is the output in this way. The control data goes here, data goes here, and when this interact with each other, if control is 1, the target is. This is very simple logic. Actually, you can use this logic, for example, to build this circuit. So the control target, then the control flips the target, then the control flips the target. This very simple matrix, this very simple circuit is a swap circuit. We can use it to swap this A and B without using a temporary variable as we used to do in the programming languages. We can build many circuits using this. For example, this Toffoli gate, it has 2 controls and 1 target. So if these 2 control qubits are set to 1, then go and flip the target. actually this very gate is proved to be universal for quantum computer. So anything we can do on classical computer, and this answers the question which is powerful. So this gate shows that we can do whatever we do on classical computer, we can do on quantum computer, plus other things quantum computer can do. So because we can build all the logic on classical computer using this gate. We can build all the logics from classical computer directly on quantum computer. For example, these very simple gates, this is the XOR gate, for example. So we can we have XOR operation, we have OR operation, but in a reversible way, of course. We have AND. Where is the AND gate? You can try to find this is the AND gate. So all the logic we do on classical computer, we can do on quantum computer. That's why classical computer is a subset of the quantum computer. Anyway, I will not go deep in this because it is a long story, but I'd like to hear questions after we go on quantum computation. Is there any questions?
Yes, perhaps Dave, we haven't heard from you. So why don't you take this one?
Very good. This is the question from George Z.
Yep.
Very good. George Z has a question. Is that space complexity, not time complexity, of quantum algorithm can be worse? Not a problem in superposition, but exponentially larger when unpacked to classical computer. Currently needed to communicate with quantum computer.
I'm not sure if this question is correct, because it carries a contradiction, right? So you say the space complexity of quantum computer is worse than classical computer, because when we unpack the data from quantum to classical, we will need a lot of space on the classical. So I think this is not correct. Quantum computer, we can back a lot of data on very small space, but when we unpack the data on a classical computer, we will need that amount of space. So it is not worse, it is better. You showed that it is better. Classical is worse in this case.
I would say that in general, this may be talking about the noise barrier going from the classical to the quantum. And that certainly is an issue. So whereas I agree with
okay, you mean okay, yeah, I got the question. Actually, this is again the matter of time, matter of technology. On quantum computers till now, we have to do the same thing more and more and more, again and again and again, in kind of shots until we get probabilistically the result, if this is what I understand. Yes, you are right. But again, this is not quantum computing. It is the architecture, how we build the quantum computer.
Yeah.
And I can assure you that this is enhancing rapidly. This noise control is enhancing. So it will be no problem very short.
Yes. And in fact, my understanding is, Dr. Khan, you've done some foundational work in noise reduction.
Thanks, Dave. Yes, there's this idea of Nash embedding that I've been kind of, trumpeting around, if you will. And I think that famous theorem of John Nash, the other one, not the one that got him the Nobel Prize, could address this question of how do you make, physically architecture, as Professor Younes is saying, architecture that implements quantum computing but lives inside the classical world, right? In a noise-free fashion. So certainly, as I agree with Professor Younes, there's a lot of developments that are taking place, but there's also this limit of, like, when you increase the number of qubits, you start seeing this noise get worse and worse. So certainly technological and engineering ideas are being used for that to mitigate that. But I think some deeper understanding would be required perhaps at some stage, you know, from a formal design point of view. Absolutely.
Mhm. If I may ask a question from someone who I know, there is Sharanya, who goes by Sharon. Sharon is a circuit designer, and I know her as a person who has her soldering iron, and she is interfacing on behalf of Centennial College, a Toronto college, where they design CAD and CAM, computer-aided design, computer-aided manufacturing. So this is a hardware question where I've been asking her in terms of support for what we're working on at Darkstar. And the question here is, dear professor, can you share your experience about your work on designing quantum circuits for Boolean functions? I think it would be inspiring.
Thank you very much for this question. Actually, I skipped this because if I start this, the lecture will end without concluding. But actually, I can show you how to do tricks, another tricks on classical computer. To if you are going to use, for example, try to use any quantum computer to simulate any Boolean function without any knowledge, deep knowledge in quantum computer. So you can build quantum computer just from the truth table. For example, if you have truth tables just like this, x1, x2, and this is f. This is a truth table, 0, 0, 0, 1. So let's invent any truth table. You can do this, the same technique on any Boolean function. So for example, let's say this is a truth table. So to build a quantum circuit directly from the truth table, just take the rows that evaluates to true, and it takes the controls from the x's as a control. So here we need 3 qubits, x1, x2, and f. So we need 3 wires, x1, x2, and f will initialize to 0, it will end it with f. So now take this as controls, but the control with their values. So they will be open. So you can create TOEFL here, 0, 0, open, open. Always the target will be on this. Here, 1, 0. So it will be closed because it is 1 here. 1, open. So now you have a quantum circuit that evaluates this. Maybe it is not the most efficient quantum circuit to do the job. So actually you can use the Boolean logic to optimize the circuit, but you can have you have now, without any background in quantum computing, you have a working quantum circuit that can be implemented on, and leave the job to the transpilers of the quantum computer. They will optimize it for you. But actually, you can optimize very easy, because this logic is equivalent to x1 bar, x2 bar, not x1, XOR x1, x2 bar. So this is the Boolean function equivalent to this. Using a few optimization steps, you can, let me take 1 minute on this. So this is x1, x2 bar. We know from the principles of modulo 2 algebra that actually x1 bar equal x1 XOR 1. So we can just do very quickly, sorry. Actually, this is my first PhD paper, so it is my favorite. It is my first published paper in 2004. So we showed this very close connection between this Boolean quantum circuits and Reed-Muller logic, and it was very interesting. Actually, very excited to publish this paper. It's my first paper. Maybe I don't remember many papers after that, but this one I cannot forget. So this is the bars after XORing. So if you multiply them quickly, x1, x2, XOR, x1, XOR, x1, right? And again, from the from the properties of the modular 2 algebra, if we have two mean terms like this similar, we can cancel. Every two can be cancelled with each other. So we ends up with this circuit, which is x2 XOR 1. So actually, this is equivalent to only this circuit. So using classical logic, we can prove that actually this very complex circuit is equivalent to this quantum circuit. So it was open, right? Let me check. Okay, it was closed open. So the quantum cost of this circuit is 10. The quantum cost of this circuit is 2. So you optimize using without any background in quantum computing. It is just logic. So it was very interesting, this work actually. Okay, let me go because we are running out of time, I think. Let me talk quickly on quantum searching because it is really important. It has been used to solve many problems and still being used to solve many problems. Just to mention that quantum searching, to search on a classical computer, you have many ways, many possibilities on a on a classical computer. So you choose to go to this path. If it is not working, you will go to another path and so on. But using quantum computer, you can, using superposition, you can search using over all passes. And the trick now is to, because the probability is distributed now over all the positions, but the trick is to increase the probability in the position of the solution. One of the maybe the first quantum algorithm to solve this problem is Grover's search algorithm. I will not go on the details of the mathematics, but I'd like to show you that what we do to amplify the solution. By amplification of the solution, we mean that we increase the probability to find the solution when we open the door, because it is like a children who is in a room alone and he's jumping here and here and there. And when you open the door, you will find that children, okay, he will sit down to the nearest chair to show that he is polite and he's not doing anything bad. And this is the same trick we use on amplitude amplification. That you put some toy to mark this place with his favorite toy. So when you open the door, you will find him on this spot with high probability. So this is the amplitude amplification to trick the data to be in certain place. So let's start. I will go very fast with this, but just to show you that what Grover's algorithm do in very simple steps. So we will start with all possible positions. This is a superposition, and this is the toy thing is to mark the solution with this -1 or phase. This is a phase shift. We call this phase shift by an angle pi. So again, you start with all the possible solutions and you have an oracle. This oracle knows the solutions, but it is unknown. It is a black box for you. You don't know what is the solution of this oracle. So the oracle is to mark this. If you mark this and you apply Grover's operator, actually the probability of this item will be amplified, and the probability of the other items will be de-amplified. Why? Because Grover's algorithm do a very simple operation, which is will change the amplitudes of the solutions using every single amplitude will be changed using this equation. This equation says that every amplitude will be subtracted from the mean of the amplitude. Okay, what is the mean here? So you have here 8 states, 7 of them with a positive value, 1 of them with negative value, right? So the amplitude is 7 with positive sign plus 1 with negative sign over their number, right? So this is the amplitude. Now take every positive amplitude of these and apply this formula. So we'll find that the new value is de-amplified, and only the negative one will be amplified. So after applying 1 iterations of Groover, all the probabilities, all the amplitudes will be de-amplified. Only the one marked is amplified. So it is really easy math to do this, to calculate the amplitudes and just subtraction and addition. This is how Groovers work. To visualize this, because maybe mathematics is not the best way to explain it. So we start here with all the possible states. After 1 iterations of Groover's algorithm, you will see that the probability of the solution, here the solution is 7, for example. So the amplitude of 7 is getting higher. Again, after another iteration, it will be higher again, and so on. So after 3 iterations, we can now open the door with very high probability. You will find your kids in this position, because this probability is 99 point something. But we have using this is something quantum unknown behavior. No one can understand why, but mathematically you can understand. But why it happens physically? Actually, I have been in this discussion for a very long time. But anyway, what's the problem? The problem is that if you want more probability, you expect to do more iterations, right? But this is not the case in quantum computing. The next iteration will make the amplitude decrease again. It's not something we want, right? To do more effort, but we will get less probability. So on the 5th iteration, the probability will decrease again. Actually, why? Because this mathematically it has been proven, because the probability goes in the sine wave, so it is increasing and decreasing. So we have to be very careful to open the door and measure the result when the probability is on its top. So don't do more effort to get higher probability of the solution. Actually, there is a nice competition in this, and our group has a good rule that people are trying to invent quantum algorithms to get probability, the search with higher probability, always with higher probability. So Grover's algorithm, actually the original Grover's algorithm, can reach 50% in some cases. And we have some contributions here, and the last record is ours. Actually, we can reach with a solution with this probability. So this is one of our favorite subjects, the quantum search algorithms. Another application, but before I start this, I'd like to take questions if we still have time.
Yes, thank you, Professor Younes. I'll take these questions or read them out if that's okay with Dave and Nada. Awesome. So there was a follow-up question from George Z. Zipperlin, who had asked earlier the question about what happens in terms of the implementation of quantum computers when you try to realize them in the physical space, like, they become complicated to deal with. The question he's following up by saying, is this a problem in the NISQ era, which is the current era of quantum?
Yeah, the problem is in the scalability, but actually this error in quantum computer, it turns out to be useful. So we can solve good problems in the presence of noise. So yeah, this is the current technology.
Wonderful. Thank you so much. So there's a question from a Zoom caller, just an anonymous person, I suppose. Professor, please, could you talk about quantum memory and how this would play out? Would there be trapped cloud of particles, etc.?
Actually, the quantum memory, this field quantum memory is very big, and it has special treatment to to store the data and to retrieve the data from the superposition. So it will take very long time. So I apologize for answering this now. It is a little bit tricky problem, this quantum memory, because especially in the existence of entanglement. If you try to filter data from a superposition, it still be in an entangled with another state in the superposition. So this is a little bit tricky subject to talk about now. I think it's not for the beginners level. So.
Thank you, Professor Younes. There's a question about whether you can put a link to your paper.
Yeah, sure. I will send you the link and you can share with all the attendees. Yes.
Wonderful. Thank you so much. So those are the only questions that I think are that are open. We have addressed those. So Professor Younes, please go ahead. Continue.
Okay.
Please. Thank you.
So more about applications in quantum computing. Very quickly, I will just mention, answer the question about cybersecurity. Actually, the bad news is Shor's algorithm break our RSA encryption algorithm. The good news is that we have an alternative on quantum computer, which is quantum key distributions. We have many techniques to encrypt data on quantum computer. And the good news is that this data is somehow unbreakable. We cannot break the encrypted data. Maybe quantum key distribution, the first one is okay. We can break it somehow, but there are many quantum encryption algorithms which were proved to be unbreakable. So okay, we are replacing again the encryption and the security over networks. Again, this is quantum teleportation. It is a communication protocol between two parties, Alice and Bob, by which we can transfer quantum data in a superposition from one point to another. All these the protocols has been applied for very long distance. Quantum dense coding is my favorite because it says that actually whatever the speed you can achieve on classical computer, on classical networks, we can always double this speed because it sends 2 classical bits using only 1 photon. So the quantum people are saying to the classical people, okay, do your best to increase the speed of the networks. We can always double this speed using quantum dense coding, which is very simple protocol. Actually, we have many quantum computers in market now. I'll just mention them very quickly. We have D-Wave, we have IBM quantum computer. IBM you can use using the cloud. You can start working on it today. This is I'm run out of time, so I will go quickly. This is Google quantum computer. This is Cirq, the programming language for Google. Xanadu is a photonic quantum computer. Actually, in our group, in Alexandria Quantum Computing Group, we are interested in IBM, Google, and Xanadu. Not much on D-Wave. I'm so sorry, Nada. But these are very good quantum computers you can use. You can try today if you are interested. The good news is that the quantum cryptography companies are there from a very long time. This technology is well established actually from maybe quantum computer as a quantum computer is still a new technology, but quantum cryptography are there for maybe 15 years or something. And there are companies who can sell these quantum devices. Just to mention some companies to tell you that this field, this industry is old. It is not new like quantum computing. It is so. If you are interested in quantum, in cybersecurity or encryption or to secure communication between two parties, I recommend you to start working on quantum cryptography. Finally, who we are. This is still another companies. So this is well-established industry. Who we are Alexandria Quantum Computing Group. I'm really sorry that we didn't have many groups in the region yet. So we are maybe the only group in Egypt. We are trying to disseminate this information. We'd like to see many groups all over the world, not only Egypt, not only the Middle East, but all over the world. This is our address. We are in Department of Mathematics and Computer Science, Faculty of Science in Alexandria University. This is our website. If you are interested, you can check our activities. We are open to cooperate with everyone. We don't have any limitations on this. Finally, I'd like to thank you. That's all what I want to say. And I'm open to any questions or discussions. Let me drink some water because I'm really thirsty.
Well, before we go into questions, and they've been piling up, and Faisal, I'll ask you to address them. Nada, let's have a little chit chat about Professor Younes' presentation. For myself, I was thrilled in that I learned new information. You took a ground-up level, and you also provided analysis. For example, looking at the green, where should I put my time and energy in terms of quantum focus? And then you differentiated that in terms of quantum this, quantum that. And the questions showed up, which we answered some of them, but there's more. But I thought you did a great job with that, and the great balance of time. Also, as a mathematician, a trained mathematician, I have a humble bachelor degree in math. I was thrilled to see you go into the mathematics component, walking us through. That solved one of the questions that I had. So appreciate you being a professor who does those
Stay away from the eigenvalues and eigenvectors.
Well, you made it so simple.
Okay.
You made it so simple with your use of vectors.
Actually, we used to do this when we design quantum algorithms, because doing a lot of math, you have to do it with your eye to understand what is the logic, what's going on.
Yes.
So
yes. So I learned a few techniques there, and I think
glad.
Others have realized, oh, this is going this way and that way, and there's patterns here. So I encourage those who are interested for that reason, and would ask for those who are interested in more about this pattern approach. Please give us some comments. It's the sort of thing that we can follow up with our collection of quantum computing group here at MISA, as well as York University, for example. So those are my initial comments. And I have more, but I'm not going to take up the time now. Perhaps, Nada, we can have your thoughts and then turn it over to Faisal for more questions.
I think it was very engaging because I'm new to computer science, relatively. So my undergrad is in math, but right now I'm doing a master's in computer science. So it was very cool to see all of the different things that I'm learning right now with respect to quantum that I never knew before. And also my current thesis is to do a deep learning, and I never actually thought about quantum deep learning. So that's definitely something I'm going to be deep diving into tonight.
You'll find many publications in quantum deep learning.
Very excited. But yeah, also I'd like to mention that my cat did wake up, and she was very, very, very noisy, but I'm really glad nobody heard.
At last we can see your cat.
I mean, she went back to sleep. I feel like I sound like I'm lying when she was walking around screaming everywhere.
She was excited with the talk, maybe?
Very excited. I think my headphones died at some point, so then she could actually hear the audio, and she was like, oh, there's stuff going on today.
Let's thank you.
So your cat must be descended from Schrodinger's cat if it enjoyed Professor Younes's talk, right?
Yeah, definitely.
Wonderful. So let's look at the questions, Professor Younes. There's a few more questions for you. we can start with, there's a question from Adam that says, what happens when the search algorithm fails? The time and space complexity of running many parallel searches, and comparing their results seems greater than those of a classical search. This is pertaining to Grover's search algorithm.
Yes, actually, that's why there is a big race to invent new search algorithms with higher probability, because it is a probabilistic algorithms. So we have to do it again and again. But if you have a high probability of success, you don't have to do it again. And you can check. There is always a check a way to feed this result to the Oracle again and check the result, only this result, and you will see if this is a correct result or not. So there is no way using this scenario that the search algorithm will fail. So you will run with higher probability, get a solution, feed to the Oracle and check the result. If it is not the result, do it again. And because it is fast with and high probability of success, so eventually after, I will not say in certain number, but after a few trials, you will have a solution, of course. So it will not fail. That's what I say.
Thank you, Professor Younes. There's a question from Samuel Keating, which is, what do we know about the quantum operating system recently developed in China?
Actually, I shared this on the page 2 days ago, and I didn't read it yet. So I will go and read it because I didn't have time. But I'm really interested to know what's this quantum operating system.
Thank you. If I may kind of, say a few words about that, my words would be, operating system for which quantum architecture, I guess, hardware platform, right? Is it? So presumably China has developed something like D-Wave or IonQ or IBM, etc. So this would be an operating system for whatever they have, or is it for the hardware architectures for D-Wave, etc., for example. Again, I haven't read it in detail myself, but that would be
but it is in my list. I will read it very, very soon. So I cannot answer this question. I'm so sorry, Samuel.
I'll try to have a chat with you afterwards, after we've both read the article carefully. Thank you so much.
Thank you.
So here's a question from Barry Bird. What's topological, point set or algebraic, about computing with anyons?
I did not understand that was a question.
It's the question is about what kind of topological, what aspects of topology are pertinent to computing with anyons?
Topological qubits used by Microsoft.
Yeah.
Actually, I'm not a fan of these qubit things, this topological qubit, because there is no proof that it is working actually. So I will not comment on this.
Okay. Well, let me just point Barry to a news article that showed up a few days ago, in fact, where
something hypothetical. So yes, there is no implementation, no proof that it is actually working.
In fact, there was some, Professor Younes, some indications, I think, some time ago that they had detected anyons, right? Yes. These are particles that, as you said, there had been no proof yet, as of yet, but there were some indications they were seeing them. But then I saw an article recently which said that indication turned out to be an error. So we're back to square one as far as topological quantum computing with anyons is concerned. Unfortunately, because, I was excited because there's a lot of, nice robustness properties to these things, hypothetically, as you said, right?
Yes.
Thank you so much. Let's take a look at, there's a question, how to reach out to you, please.
How to?
Reach out to you, contact you.
Actually, I'm on LinkedIn, and this is my email. I will be glad. Let's go to end. So this is my email, and I'll be glad to receive any questions.
At the bottom of the page? Right there,
Yes,
yeah.
Younes at alexu.edu.ag.
Excellent. Thank you so much for that. And then we have a comment which says that I guess he's talking about Zhu Zhang. This would be the Chinese architecture for quantum computers. That's perhaps the name of it. So for attendees and everybody else who's interested, please go ahead and take a look at
Yeah, thank you
Zhu
for this.
Zhang in Google, and we'll see some results on that. I guess that is it for the questions that I'm seeing so far. Dave, do you have any few words? You're muted though.
There it is. Thank you. I do. It's really thrilling as a math geek, Professor Younes, to see the level of questions. And one of them that came out that I've asked the Zoom caller to contact me privately is where I had mentioned patterns. You have given a wonderful way of determining patterns, and there's a request for more suggestions. So what I request is the four of us get together and do a little bit of a pattern matching. We'll pick your brains. Because I think what you're doing here, Professor Younes, is you're finding that pathway through everything that will give us clarity. This is the feeling that I got. And one of the things that was really exciting for me was you said that there is a way of catching the probability when you want it. I'm paraphrasing here.
Yeah, actually, maybe this is another talk. The quantum algorithms we invented has little tricks more than just an amplitude amplification.
Yes. So
yes.
this is a way of getting what you want. It's a very exciting
in
process.
Quantum computing, you cannot always get what you want.
True.
Yes.
True, absolutely.
Yes.
But you're giving us a way of being efficient. Again, it's more of this cutting right through. It's the same theme.
Yes.
And I just wanted to validate one thing. You had the example of little children running around, but then when you look in, they're there. So what occurred to me here is on our panel, Nada is the youngest here, and Dr. Khan used to teach Nada. So I'm kind of curious at any point, Nada, if you could please verify, were there ever times when Dr. Khan wasn't looking and you're doing this? And then when you looked, you snapped back.
Yeah, Nada, tell us. Did that ever happen?
I have to fess up now.
Yeah, actually, he can, as a supervisor, he can amplify this or de-amplify this.
Yeah. Usually amplify.
Yes.
Oh, no, it was always very, very engaging, and I was always very, very alert.
Well, let me add that Nada is actually definitely like, her energy level is like that kid, and I love that analogy that Professor Younes gave. I'm going to use it, in my discussions from now on. But yeah, and Nada has a very high energy level, and she was all over the board. I would make her go to the board and do the problems. And it was a joy to see her, do all those things, the energy level and the mathematics, of course.
And they're coming in every week going, it's all wrong, and then figuring it all out.
I would classify that as what Nada was showing us how to be in a superposition. Well, yes, that perhaps Nada, you represent those with high energy and can do everything at once. And when you have a good professor, when you have a good company, it can help guide that energy to be able to achieve the goals where there might be multiple in your head. And this aligns with Professor Younes with us finding that path while we superposition, bounce back and forth, which is a satisfying way to go. And I would say, Nada, you represent youth and energy and brilliance with your work on that little company called D-Wave with your portfolio optimization. And you represent a practical application of all this. So I wanted to close my comments off with that. I'll turn to your closing comments. and then turn to Dr. Khan to close it off with you and Professor Younes.
I just want to thank everybody for being here and letting me be a part of this. It was nerve-wracking, but very exciting, and definitely extremely informative. I think I didn't realize how applicable quantum computing was. I think I got stuck in my one little problem, and I didn't see the bigger picture. And this was very, very eye-opening. So I thank you very much, Dr. Ahmed Younes, for all of that. Thanks.
Wonderful.
Thank you very much. Thank you.
Professor Younes, any closing comments?
My audio is a little funky. I'm so sorry.
I'll stop my screen now. I think Dr. Faisal would like to share something.
Yes, absolutely.
Remind you or not, yes.
Thank you so much, Professor Younes. It was a great pleasure to have you speak.
My pleasure, and I'm honored to be invited. Thank you very much.
And we hope to have you again, given how good you are at this.
Yeah, thank you very much.